Hi everyone, this is Professor M. Science, and today I want to discuss measurements in quantum mechanics with an emphasis on the mathematical details. This is another one of our videos on rigorous quantum mechanics. In the companion video linked in the description, we explore the conceptual understanding of measurements in quantum mechanics. In that video, we find it's impossible to predict the precise outcome of a quantum measurement. All we can predict is the likelihood of a given outcome. Today we start with that conceptual understanding, and then we expand it to explore the mathematical subtleties associated with, for example, degenerate eigenvalues or a continuous rather than a discrete spectrum of eigenvalues. Let's go! We consider a physical quantity A that in quantum mechanics is represented by a Hermitian operator A called an observable. We call the observable A to keep the discussion general, but for concreteness you can think of this as, say, the energy or the position of a particle. This observable A obeys an eigenvalue equation as shown here, where lambda n are the eigenvalues and un the eigenstates. In the companion video on measurements, we introduce postulate 4 that tells us that when we measure A in a system in state psi, then the outcome of that measurement is an eigenvalue lambda n of the operator A, and I will get that result with probability given by this expression. We can find an alternative form for this probability if we write the state psi in the basis of eigenstates un of the operator A as usual, and the expansion coefficients c are given by the projection of psi onto the u basis states. This means that we can also write the probability p of measuring eigenvalue lambda n as absolute value of Cn squared. In the companion video on measurements, we go into some detail about the conceptual understanding of this postulate. So if you haven't seen that video yet, I recommend that you do that first and come back to this video afterwards. What we want to do in this video is to unpack some of the mathematical details of postulate 4. They don't affect the conceptual understanding of the postulate, but are useful for calculations. The main point is that when writing postulate 4, we're implicitly making a number of assumptions. The first is that the state psi is normalized. The second is that we're assuming that the eigenvalues form a non-degenerate spectrum. And the third is that the eigenvalues form a discrete spectrum. What we'll do in this video is to investigate what happens when we relax these assumptions and how we then have to update postulate 4 accordingly. Let's start with normalization. Postulate 4 tells us the probability p associated with every possible outcome of the measurement. However, when we measure A, we will get some outcome, so this means that the sum over all probabilities should add to 1. So is this the case? Let's calculate the norm psi of the state of our system. We can then write both bra and ket in the u basis as usual. We can move the sum over m to the beginning, and we rearrange the expression to get this. The bracket here is delta nm, because the u states form an orthonormal basis, and this means that we can easily perform the sum over m, and we end up with a single sum over n of the absolute value squared of Cn. Looking at the probability up here, from postulate 4, we see that this is simply equal to sum over n of the probability of measuring eigenvalue lambda n. So what does this mean? If the state psi is normalized, then we correctly get that the sum over the probabilities of all possible outcomes gives 1. However, if psi is not normalized, but instead this bracket is equal to some other value n, then the probabilities as written in postulate 4 don't add up to 1. To ensure that they do add up to 1, we need to modify the probability and rescale it by the normalization n. We can also replace the norm by the bracket of psi with itself, and we get this final expression. So this is telling us that we can generalize postulate 4 to the case where the state psi of the system is not normalized if we use this expression here. With this more general expression we have just derived for the probability of measuring lambda n, we can now clarify a point that we first made in the video on eigenvalues and eigenstates. Let our system be in state psi. Then the probability of measuring lambda n when our system is in state psi is given by this expression we just derived. In this expression I have written this subindex here to emphasize the fact that the state of the system is psi. Now let's construct a new ket psi prime equal to r e to the power I theta times psi, where r is a real number. Psi prime is related to psi by changing its length by a factor r, and its phase by an angle theta. The argument we made in the video on eigenvalues and eigenstates was that quantum mechanics is not affected by such changes, and that psi and psi prime lead to the same physics. We're now in a position to confirm this by checking that the outcome of a measurement is the same whether we use the state psi or the state psi prime. The probability of obtaining eigenvalue lambda n when the system is in state psi prime is given by this expression. And again, I emphasize that this corresponds to the system in state psi prime with this subindex. Now let's rewrite psi prime in terms of psi, and in doing this remember that we need to take the complex conjugate when we work with brass in dual space. In the denominator, this exponential cancels with this exponential, so this term is r squared. In the numerator, the absolute value squared of these two terms is simply r squared. This means that this r squared cancels with this other r squared, and overall we get this expression. Comparing this result with this result, we see that the probability of measuring lambda n when the system is in state psi is equal to the probability of measuring lambda n when the system is in state psi prime. This confirms that predictions in quantum mechanics are independent of scaling and the phase change in our state. We next want to look at what happens when we have degenerate eigenvalues. If lambda n is a degenerate eigenvalue, then the eigenvalue equation at the top here needs to be updated to A acting on uni equals lambda n uni, where I runs from 1 to gn. We have already encountered this eigenvalue equation for degenerate eigenvalues lambda n in the video on eigenvalues and eigenstates. It is telling us that there are gn eigenstates that share the same eigenvalue, and these gn different eigenstates are labeled by the index I. You'll remember that the eigenstates associated with the degenerate eigenvalue lambda n span a gn-dimensional subspace of state space, and we can always make linear combinations of these eigenstates to get equally valid but alternative bases. Exploiting this fact, we can always choose these eigenstates to form an orthonormal basis, and we can therefore expand the state psi of our system in the basis of eigenstates of A. In this expansion, I have explicitly separated the sum into two terms, one over the distinct eigenvalues labeled by n, and then the other over I, taking into account the degeneracies of a given eigenvalue. This also means that the expansion coefficients C now have an extra I index, and this of course follows from the fact that the expansion coefficients are given by the projection of the state psi onto the uni basis states. So in this case of degenerate eigenvalues, the probability of measuring eigenvalue lambda n as given by postulate 4 needs to be updated to the sum over the gn-dimensional degenerate subspace. And again, we can rewrite this directly in terms of the expansion coefficients C. What I want to discuss next is how we can rewrite the probability of the outcome of a measurement in terms of a projection operator. Although this is a less familiar expression than the one we have been discussing so far, it is very convenient in some cases, for example when discussing the density operator, so it is definitely worth going over it. Remember from the video on projection operators that we can write the operator that projects onto the gn-dimensional subspace of a state space spanned by the basis states u and I as Pn, and it is given by the sum of the corresponding subspace of the outer products of the basis states. Imagine that our system is in state psi, and then construct a new state psi n as the projection of psi onto the gn-dimensional subspace associated with eigenvalue lambda n. Writing the explicit expression for the projection operator, we get this. This here is the usual expansion coefficient C, so we can then rewrite the state psi n like this. Let's now consider the norm of psi n. Using the expression we just got here, we can rewrite it in terms of a sum over I, and then a sum over j. As usual, we can move the sum over j to the beginning, and we rearrange the expression to get this. The basis is orthonormal, so this is delta ij, and we can reduce the double sum to a single sum over I of the absolute value squared of Cni. Comparing this last expression with the one up here, we see that they are the same, so this is simply the probability of measuring eigenvalue lambda n. So what does this mean? We can rewrite the probability p lambda n as equal to the norm of state psi n. This in turn is given by the projection of state psi onto the Gn dimensional subspace associated with eigenvalue lambda n. Projection operators are Hermitian, so this is equal to Pn squared. Projection operators are also idempotent, so Pn squared is equal to Pn. And overall, this means that we can rewrite the probability of a measurement outcome as the expectation value of the projection operator Pn onto the subspace spanned by the eigenstates associated with the eigenvalue that we're measuring. As I said earlier, this is an expression that is not so common, but if you want to see it in action, check out the video on the density operator. The final thing I want to look at is what happens when we have a continuous eigenvalue spectrum. In this case, the eigenvalue equation is A v alpha equal to alpha v alpha, where the eigenvalue alpha is a continuous variable. Again, we can expand the state psi in the v alpha basis, and the expansion coefficients are still given by the projection of psi onto the basis states. From basic probability theory, when we have a continuous variable, we need to work with probability densities rather than absolute probabilities. We therefore look at the probability of getting a measurement outcome in the range between alpha and alpha plus d alpha. We call this probability dp alpha, and it is equal to the absolute value squared of v alpha psi multiplied by d alpha. This in turn can be written as usual in terms of the expansion coefficients like this. So what does this mean? For continuous eigenvalues, the absolute value squared of the expansion coefficients gives the probability density at that eigenvalue. And to obtain actual probabilities, we must first define a range of possible outcomes, say an infinitesimal range d alpha, and then in this case multiply that range by the probability density. If instead of an infinitesimal range we have a finite range, then we integrate the probability density over that range to get the total probability. The most famous example of a continuous variable is perhaps position, which leads to the position representation. Restricting the discussion to one dimension, a general state psi written in the position representation is given by this. The expansion coefficients are still given by the usual expression, but in this case they are typically written with the symbol psi rather than the symbol c. Of course, these are nothing more than what we call the wave function of the system, and you can find further details about this in the corresponding video linked in the description. What this discussion teaches us is that when we work in the position representation in terms of wave functions, the absolute value squared of the wave function gives the probability density of finding the quantum particle at position x. And this of course is an elementary result that many of you will probably recognize. Measurements in quantum mechanics introduce the famous probabilistic nature of this theory. This leads to many strange phenomena, but I would say this is also what makes quantum theory so exciting to study. You can find many videos in the description and in the channel where we explore the weird consequences of measurements, so do check them out. And if you haven't yet seen the companion video where we explore the conceptual understanding of quantum measurements, go take a look. I think you'll find it really interesting. And as always, if you liked the video, please subscribe.